Screen. Okay, good. So today I would like to discuss. So there are two things, right? The first thing is the very long question of how do you put these two words, computation and design, together? Is the first question. And the second thing is, how do we really use it, right? Because people get interested in new technologies, new trends, but do they really help us create value and meanings, right? So that's the primary kind of discussion about this presentation, and it has been the kind of like pretty much the basis of all my presentations and discussions. So I'll start with the simple examples that I love a lot and show a lot. Is if I ask you if the point is inside or outside the closed curve, you can immediately tell that, right? Because it's human perception and you know the rules of being inside or outside. But if you need to describe this as a problem to the computer, then you need to use a technique. And in this case, there is this ray intersection technique in which you draw lines or rays out of the point, and you count the number of intersections with the curves. So in this case, if the number of intersections are odd, then the point would be always inside. If all the intersections are even, then the point will be outside, right? So you kind of like tell the computer, okay, don't look at the thing because you cannot see, but count the numbers and tell me if the point is inside or outside. So there's a shift here, right? So what happens is the question of being inside or outside becomes the question of being even or odd number, right? So suddenly we unsee, right? So the human's vision is destroyed. It's not there anymore. But seeing is reduced pretty much to counting by the computer. So it can detect if the points are inside or outside. So we are looking into this kind of dichotomy, right? So there's a tension here because we are working on the meanings, understandings, but we are talking about representation, which is a limited world actually, not a word, but a world. So meanings are in this sense, we can say meanings are about design, whereas computation deals with representations. And as you're kind of like drawing the cycle between design and computation, you have to find ways to use the knowledge, intentions, and meaning for design and convert them or use the means on the computation side, which are representing, sensing, and making, right? So you have to find a way to bridge these things. So that's my brief intro about human vision, what humans can do, what computers can do, and how they really do it for their parts. So I'll jump to this and show you a video, and then we will keep the conversation after that one.
The future of additive manufacturing is really the ability to create high-performance parts for athletes, to be able to manufacture on demand, and really be able to customize for the individual athlete's biomechanics.
Yeah, and with additive manufacturing, we believe that we're going to be reducing R&D timelines as well as production timelines. There's going to be on-demand and regional manufacturing that's going to allow us to reduce lead times as well as reduce the amount of shipping of product all around the world.
Triple Cell is our new technology platform created with 3D printing.
When we started this project, we knew we needed a very specific material. It did not exist in the 3D and additive space.
We knew we were going to need a great partner to help us bring this to life.
Yeah, unfortunately, just 4 miles down the road from our Brighton headquarters, we found the right partner, Formlabs.
We've been working on this material with New Balance, and the goal was always to create a disruptive new material that has the extra kick that a specially designed material can get you. We specifically formulated a material that has very high elongation and a lot of energy return.
Unlike foam cells, which are made with chemistry, Triple Cell is made with computational design and data, which allows us to produce precisely shaped and sized structures.
The real magic of Triple Cell is what our own internal design team brings to the process.
We literally started developing methods that don't really exist for additive manufacturing. And it really enabled us to iterate and reiterate and reprint so many parts. With the foam, we designed a part and make some engravings on the surfaces. Whereas with the 3D printed parts, it's like carving. We designed the volume, like what we take out from the space.
We can adjust in any local region the structure to address different aspects of the foot strike, for example. We can really take a more supportive structure, for example, what's on the rim of this part, and we can blend it with like a more cushioned structure, for example, what's in the core of this part. One day we can really do that on a person-by-person basis and offer a completely unique ride for every individual.
The world is changing. People want custom things made just for them that have higher performance, that can ship overnight. We've been working together with New Balance, figuring out how we can go from a prototype footwear all the way to small batch manufacturing and then all the way to mass manufacturing.
We can take all the output from our pilot manufacturing line right now and take it down only 2 floors from where we're sitting right now and assemble into a full shoe. The ability to turn that quickly is going to be a great advantage in the future.
Triple Cell is really on the leading edge of bringing New Balance domestic manufacturing into the digital age. We've really traditionally been involved in what have been really analog and manual operations, and this is a huge opportunity for us to move into more innovative products that are produced domestically.
Through Triple Cell, we're making huge advancements. We're really going to be able to disrupt the industry not only in performance, but also in athlete customization and speed to market. And one of the things that's truly unique and special for us at New Balance is that we're developing and we're manufacturing these components right here in our own factories and in the United States.
Okay, so now this lecture is going to show what the first curve and the point has to do with these kind of like shoes, right? So they're kind of like appear to be 2 different worlds, but essentially, you know, on the root, they're like really related. And this work, that the video that you have seen, is a research that went at least for 2 years, and then we arrived at 2 products, right, which were released in the market in limited quantities. And the products are it's just the tip of the iceberg because it's a representation of our learning, and more than what they are pointing out to what's going to happen in the future, right? So this video is showcasing what we learned, what we have now, but what we will be also doing in the future. So all this work, or like a lot of work in computational design now, is about data. Everybody talks about data, big data, sometimes small data, right? Dirty data, which is kind of like lots of noise. So what is it really? So interestingly, data is a tool for describing, right? So those numbers, whatever you're looking at, numbers or the graphics, they don't exist, right? So we just use them, we just make up those numbers up to understand, right? The things around us. It's like design. And we can, for instance, in this domain, if I'm measuring the pressure under your foot, that I can tell, oh, data is the thing that's found under your feet, right? Although it's not there, I can look it in a way. I can put a sensor under your foot, which is this device, actually, right? So it has these like pressure points, and measure the pressure as you're running on the course. So this enables me, let's say, or in this kind of case, the sports research lab of New Balance, to extract those pressure values by using these little sensors under your foot. And then what happens then, right? So you get a lot of numbers from data collection, and it's a big thing, right? So you have to kind of go back into it and clean it up, but at the same time you have to look into the portions that you can really use for design. So what do you do with data? So the idea behind this is, you look at something, you split the world, right? So you don't understand running as a full action because all the body is included in it, right? There's wind resistance, there's traction, there's propulsion, and so on. But there's a portion that you can look into. So you split the world into parts, and then use that data or use that understanding to make a whole, like create something out of that. And the way this happens usually nowadays is you have the numbers, you have a way to parse that, process that data, and then the world that you discretize by numbers, you can map forms onto it, right? So this has been around for a while. All the generative design or parametric design things that you have been seeing for the last 20 years or more is influenced by that. There are numbers in space and you map shapes on them, and this is pretty much called like algorithmic design, right? Essentially, it looks smart, but mechanically it's not that smart. It's just a number and just the shape on top of it. What is smart is what you can do with it, and if you can really generate the meaning with that is very important. And as I was discussing, you don't look at the full picture, right? You cannot look at the full picture. So you always attend to a portion of the thing or portion of things while you're designing. Same for building, same for interface design, same for product design, and so on. So there's always an unattended portion in your, whatever you're designing, and it's okay because it needs to be that way. You cannot really fully comprehend the full thing. And I will talk about these resources. So these ideas are not kind of like emanating out of me, right? So I'm kind of like discovering things, but also happen to read these people and I've learned from them. For instance, if you look into what David Bohm is saying in his article, Meaning and Information, he's talking exactly about that. You cannot see the full picture all the time. We always attend to a portion of the thing, and it's totally fine. That's what it is about. But beyond that, what happens in design is you use data and you use whatever you attend to for inspiration, right? So you can change the landscape. You can explore these forms. They would look different than what they used to. Some of them will be noise and won't make sense. Some of them will be different and striking because it's a new form. And for instance, in this case, you see it's a kind of like this very alien form that we are not used to, but it starts molding and fusing, which is changing what a shoe might be, right? So in this way, data or the new understanding about computing is helping us change the descriptions that we used for things. So for instance, in the past, a shoe would be as simple as just kind of these 6 components that are shown on the top left, but you can also describe it in a very kind of like mushy way, like the colorful image on the bottom right. But all those components are kind of like pre-compiled components. Maybe they won't exist anymore in the future. Same thing applies to buildings too. So in this case, for instance, we have this heel component on the left side, which is made of these multiple parts. On the right side, you have one single part, which is kind of like the portions of the 3D printed part is replacing those subparts, subcomponents of the heel part, right? So it's changing the description of what a heel component might be. Going back to the meanings and let's say value that you can create, what you can compute doesn't necessarily mean that it's going to be meaningful, although you use data. So you always have to check it more than twice, 3 times, 5 times. So you always need to see what's happening. Whatever you compute on the digital side has to have a meaning or counterpart on the real life, right? So here, the perception, the feeling is very fundamental for what you have. And you always go through these steps, more steps actually, of like computing, blending, distributing these parts, and then having an understanding of what's happening in real life. So the digital side has been always, this digital parametric design, computational design has always been very exciting. So because you can have one single shape and open up the design space by exploring different parameters and shapes, right? This is very kind of like well known now. Or you can improvise with shapes that you don't know, right? So you can kind of create these parts that you didn't witness to. You can just be experimental and so on. I know a lot of people who are listening today have been doing this for a long while in the different platforms, and they contributed to people learning about these forms, these shapes, how to make them, and so on and so forth. So this is a great audience again. And we did this too, right? So at New Balance, what we did is the maybe slightly different portion is that it needs to be very tangible and it needs to perform, right? Because we are talking about a consumer product that's going to be at the end of the day out in the world, and it needs to satisfy kind of very serious, let's say, demand from real world conditions. So here in this video, you can see around 400 plus parts out of 700 parts that we designed and printed. So we only rendered and kept these, the ones that we printed actually. So if you look into the parts that we just designed, we have maybe thousands of parts. And what we do is we design these parts, we visualize them, we We document them, we track them, we test them, and we try to understand this kind of like knowledge base, create this knowledge base so we can move forward with what we do. So in that case, it really, again, the physical part means a lot, right? So you have to go through a lot of mechanical testing, and those circles are referring to the impact tester kind of landing on that part. So we can extract that information about the behavior of these parts. And computational design is, again, not about only making these kind of like forms, shapes, and printing them necessarily. It's also about coming up with these methods of creating those things, right? So computational design is not looking into only forms and parts and buildings. It's also looking into ways of building up these new techniques, these new methods, and new design understanding, so we can, again, move forward with what we are trying to do. In this case, all those blocks that you have been seeing, this is the kind of like the pseudocode, the logic board, showing how that part is kind of like generated. And interestingly, at the end of the process, once you print and test it, you again end up with data, right? So we have these curves and charts that are showing how a part really functions, right? So this is also another sort of reading at the end of the, let's say, design phase, which enables us to look into parts performance and go back to it and iterate the design. So the first data point and the second data is totally different, but again, it's a different sort of description. These are the two structures that we kind of landed on for the two products that I mentioned. You saw them in the video. And at the end of the day, it's very interesting, again, for like, it has to end one day, right? So like designs, you have a deadline, and same thing for the products, same thing for the buildings. It has to be done one day, and it needs to be delivered in the best way possible, right? So this is pretty much kind of like pointing out that day. And you would see that both of these parts, the heel part and the forefoot part, are kind of like using these different techniques to have this visual language, right? Which is about more like aesthetics side of the design. And the internals, the guts, are doing something else about the performance of the part. And these two need to kind of like talk to each other, of course. A very similar case in the, building facades and, circulation and so on and so forth. The scale is much different though. And then, the shoes pretty much kind of like become alive at the end of the day. So it's a sophisticated process. The part is very small. Coming from architecture background, I was designing skyscrapers at some point, which was like half a kilometer tall, right? So to a part that I can hold on daily basis is a really weird thing. But if you look into the quote unquote like intelligence that is going into it, is pretty interesting. It's a lot of work, and it's, again, this is not me only designing this part, but I collaborate with so many people in the office, right? So the people who are kind of like working on the base form, the sculpting, which is more like a manual, like a conventional modeling technique. And then the people who are kind of like printing and curing these parts and making ready for assembly, right? So I have to learn from all of them and just kind of like fill in my position in the center to kind of like deliver the thing about the algorithmic design or the computational design part of this thing. And again, now the pseudocode is kind of like getting larger, right? So what I call is the pseudocode is the logic map of how these parts kind of like get together and how you generate this part. And when you zoom in, you see points like this. For instance, this orange is kind of like orange circle is referring to a moment in which I'm bridging like islands together to make part like sturdier, right? So this is pretty much happening between the sidewall and the guts, the internals of the forefoot part. And what's kind of like broken, quote unquote, here is, there's an algorithm that goes through there and kind of like bridge those, let's say, structures to have this very organic form, but also make sure that it works and it's kind of like in place. The other difference between architecture and product design is that the buildings are one-off, right? So you go through a lot of like design iterations and changes, but at the end of the day, you make one of them most of the time, right? If it's not a kind of like a site. And here, or if there's multiple of them, they're the same size, more or less. And then here, what's happening is for the design, you have to expand your model into 17 or 20 plus different sizes, right? So there's sizing from woman's 5 to men's like 15. and a part is, let's say, more than twice the, the size is twice the amount of the smallest one. And I was super psyched to kind of like work on this like one-click solution to run, all the scripts starting with the part and kind of like delivering and exporting this printable STL somewhere in the computer, right? So this kind of like an exciting, playful part of the process. And at the end of the day, this shoe was out in September last year, and got some interesting reception, so it's pretty good. This is all referring to some sort of a shift in, again, our understanding, our design methods, and our like production techniques, right? So the parts, processes, methods, and tests even are changing. One new thing that wasn't happening that much, but that is happening a lot now, and which will keep happening even more with the metal 3D printers and all these like new flexible resin printers, is we're going to work on metamaterials, right? So metamaterials are forms and shapes we make with the same material, but because the shape changes, they perform as if they are different materials, right? So this is very kind of relevant in the area and that's called design for additive manufacturing, and it's going to be an area that's going to grow a lot in the future. If you're interested, just take a note of that. What's happening again is what was fully digital is by using these tools and techniques, and printing is becoming very tangible. What we used to see online, is crazy forms. You can just print them and just see if they're, doing something at all, or if they're like, they're not really that meaningful at all, kind of thing. So again, a big change between what happened in the last 10 years is we shifted from, in terms of parametric and computational design, from surface 2D modeling to a lot of volumetric modeling, right? So even the buildings that we were working on, mostly they were like facades, some spatial distributions, some circulation simulations, but parametric design found itself as a kind of manifestation on the facades. And to be honest, I don't think it went kind of like a lot further from there. But I think now, again, things are changing, right? So for the university case, I think the one-to-one scale work is super interesting in the way that it looks into, again, the spatial manifestation of those surface forms, right? So that's a different thing. When you start moving into space, volumetric design, it's changing the idea a lot. So the surface design is simple, right? So hexagons or Voronoi patterns, they've been always there. Everybody used them. I used them, right? So for instance, for this product, it's a small tracking device. And you can see that the hexagons are ever slightly kind of like changing the depth of the part. So that was my kind of like, that was what was asked. And interestingly, that design made its way to Time magazine in 2018 as one of the best inventions, right? So it's a simple design on the surface, it works. So you can always use these techniques. But again, those ideas are coming from architecture, right? So these are some of the projects that I worked on, in which, I was mostly kind of like working either generation of these, global forms of the buildings, and sometimes going back to it and making it possible to be constructed by using flat panels, right? So because the digital world moved super fast, but the construction world kind of like couldn't catch up with that, right? So we had to kind of like find a way to build those things. And so if you would like to read more about that, especially the foundational parametric design, I would advise looking into this book by Robert Woodbury, Elements of Parametric Design, and I happen to contribute it with some of my KPF work under a section called Geometric Gestures. And at the time, of course, we were looking into not on the surface, like the panels, but also the structural members. And I ended up kind of, this is a photograph of a building that was built probably like several years ago now. And it happened to be one of the longest land scrapers in Asia. The sophisticated part was the structural configuration, in which I helped some Arab engineers to resolve what's happening with the structural members, right? So it's pretty interesting, because to make a shape like this, which gets kind of like lower and it kind of like pulls back and shrinks a little bit, the beams cannot be flat. So you have to somehow torque them or tilt them and they cannot be really parallel to the ground. So that this was a kind of like sophisticated, a problem that looks easy, but it's super sophisticated, which was also hard to explain to the clients, right? Because they want everything flat. So this slide was just proving that that world really doesn't exist in a geometric world. You either need to torque the beams or tilt them in space. So all of this is very similar to data to design idea, right? So data was about discretizing what we see and making parts by using those numbers. And this is about, again, finding some parts, some ribs, and making a global form, right? So you always go from a whole idea of the whole to parts and then to whole again. So, and this, for instance, you can represent these ideas in different ways. This is showing the architectural manifestation, the components of the building, whereas this is showing that global idea of what the form should be, right? So this is the vision about the building. Again, you know, if you look at what Alan Watts is saying, so this whole is not, you cannot really explain. You can explain it structurally, but it's hard to explain as a vision because our vision has pretty much no parts. It's just kind of like what you want to realize. Okay, so we'll take a turn here. A couple of minutes left, so I'm going to open it for questions. Two things I'm going to do. Thank you for still being here. First, we're going to wrap this thing up and connect back to seeing, which we discussed at the beginning. And then I'm going to show you some resources for how to reinforce these ideas, right? So these thinking, like how I came here, how I'm seeing these things, and how I practice, right? And the people that I learned from, I'm going to share those. And this is more on the theoretical side, right? Because technically there's so much online, you can look into that. I'm going to share the portion that's about kind of like the computational design thinking. As I'm talking, I hope that you figured out if this is a duck or rabbit, and just give you 2 split seconds to decide which one it is, because it's neither. It's a crocodile. Okay, so this slide is pretty much speaking to ambiguity, right? So the Gestalt switches you see here, you can use them, but what I'm saying is ambiguity is more generous than that. And I am not the only one who's saying it. Also, George Steiner with shape grammars, that's what he's saying too, right? So in ambiguity, you can see anything you want to see in designs too. So computers still cannot do either, right? So, and I'm the one who kind of like saw that crocodile literally there and just put it there, although the duck rabbit question is a very kind of like famous one. And here's what I'm talking about, right? So that red area that I painted is the crocodile, quote unquote, the weird thing that I can see, I want to see when I look into this, you know, like let's say regular pattern. And by using that, what I can do is I can keep seeing weird patterns starting with a simple shape, and I can talk about this painting in terms of computing or shape calculation, right? So the shape grammars is helping me in this case, as opposed to digital computing to paint using rules, right? So it's significantly different. So what's happening here is that we are we are creative, we see things, it's ambiguous, we don't know what we're seeing, but to again kind of like have the stable world of computing or calculation, we need patterns so we can construct those ideas. And now, of course, there's something new. Hey, welcome machine learning, right? So everybody's talking about AI is going to do this, machine learning is going to do that, and so on. Yes, it's going to do, you know, it's going to do some of those, but it's not going to do everything. It's not that different than, it's not a kind of like huge shift or leap in terms of the fundamental thing about digital computing, right? So here again, a visual question of how do you go from, you know, these brush strokes of oil paintings, right? And can you use computing for that? So you may have like multiple approaches to this, but what the machine learning promising you is you can't really compute, like, you know, we saw a lot of stuff, machine learning, painting, and so on and so forth. I'm not talking about that. I'm talking about the quality that you create by painting. You cannot really paint an oil painting because it doesn't matter. You know, you should be the one doing this. But you can make the machine read some patterns, right? So this is out of all those oil paintings that I was mentioning, and they're fed the style generator in machine learning, and it's giving me back these paintings, you know, digitally generated. And I'm very convinced, right? So it's not exactly what I paint, but it's similar. So it's getting these clues from, what I'm trying to do in a visual manner. So I kind of like find it successful. But at the same time, these are not really those paintings, right? So these are some patterns in the paintings which I can use furthermore for my design intentions and for my painting practice. And it's the same thing for design, right? So I can use machine learning now to generate these styles. And again, this is not a shoe per se, but it's an inspiration for making the next generation of shoes for sure. Okay, so how do you come here? What do you need to move into this world of computational design? If you look into this article that was published in Forbes last year, and they were pointing out to the skills that you would need this year. This is before COVID-19, by the way, and I think it matters more now. If you look at that list, do you see AI? Do you see computation? Do you see, machine learning? None of those are there, right? Because those tools are going to become available. It's like cars, trains, and industrial production lines, and anything. It's like internet. It's going to be available for you. You need to kind of equip yourself enough, educate, train yourself enough to be able to use those things, right? So you have to work on these skills. And the orange ones are indicating your personal skills, right? So you have to work on your critical thinking, creativity, emotional intelligence, and so on and so forth. And then, but also you need to work on these kind of like greenish, items, which is about other people. So you have to, see how you can coordinate your understanding with other people. So this is, for me, is pointing out, okay, use computation, Intel insight, right? But you need a lot of like human insight to kind of like address this thing, right? So the humans are there, it's gonna be there. And if it's not there, it doesn't matter anymore anyway. So you have to kind of like really concentrate on this part. Okay, how? Right, so let's end here. A couple of more slides. How is that the ideas that I've been talking about, you can look into these sources, and just skimming through them, just reading through them would help you a little bit, I think. The first one is this book, right? So it's talking about the impact of highly improbable. And this is one person who told, COVID would happen, right? So, and he made these predictions, and he talks about all these unexpected, events that tremendously change our lives. And this is now happening. I never gave this kind of lecture to this scale of audience ever, but because this book was saying this could happen one day, now it's happening, right? So you should always be aware of that, right? So the idea is that there is a normal distribution always. It's not that interesting, right? In terms of design too. So that's why I put those red dots outside the bell curve. So if you're trying to do something interesting, if you're trying to get somewhere with what you do, try to shoot for, out of the ordinary. Try to kind of like do something more valuable, meaningful. And at the same time, be aware that the rules may change anytime. So if you are playing with trends, what is trendy now, it may disappear tomorrow. But if you create new real value, it's going to remain. So remember that. So trend is your friend until it's not. This is also a financial advice for, a lot of financial people tell you, you can track, the charts of, in financial terms, but it's going to crash one day. The second one is meaning and information. This is a 25-page article by David Bohm. And he's talking about what meaning is. This is a physicist, so I really strongly kind of advise you to read this too. It's short, not too much. But he's talking about significance, what I've been referring to as meaning, right? So you can understand why we do things that we do and how we can, work on defining what meaning is and how we can discover significances. Another one, Zen and the Art of the Motorcycle Maintenance. Putting these two things, Zen and the motorcycle maintenance, is an interesting one. It's really happening in this book. And he's not only talking about motorcycle maintenance and Zen, but also he's talking a lot about scientific method, how we look into the world, how we split the world into pieces, parts that I was describing, how do we deal with data, and how we create quality, right? So it's beyond what the title of it's more than its cover for sure. So this will help you expand your worldview, I think, tremendously. And if you're dealing with computers, you can look into a couple of books. This is very useful for understanding the origins of computer, how they were kind of like developed. And the second book, this What Computers Still Cannot Do, is really good for showing the limitations of digital computing, right? So you can know where this is all coming from, right? So we cannot just jump, say, hey, I learned the grasshopper definition and I'm a computational designer. Go back, do your homework, learn about computers. Okay, then I will listen to you. So that's very important. Okay, so that brings us back to the question of that I included in the announcement, the poster. Okay, what is computational design? It's not new. There were so many computational designers in the history. We had multiple of them in Renaissance, right? In like 16th century. This is Albert Dürer, and it's 1514. I think he's a computational designer, and he's computing because you can see all these devices of measurement and computation, this engraving, and he depicts himself as this like angel. So this is the doppelganger of Dürer, and he or she's not doing anything, right? It's just like indifferent sitting like this. And he quoted this before doing this engraving. He said, I don't know what's beautiful. So it's kind of, for me, it's referring to beautiful is the meaning, right? So he's referring to kind of like the technique doesn't necessarily help you finding the meaning, right? So you have to still find a way to use the technique to create meaningful results. So the I think big takeaway here is be a critical thinker, right? So whatever you do, whatever you generate, computers looks interesting with data, without data, just be very critical about it and think more than twice. So, and with that, thank you for your patience, for listening to me for 37 minutes.
Thank you so much, Onur. It was again very inspiring, and many notes to take. And I am sure that there are so many questions to be asked.